evening and welcome everybody to the fifth in the series of the Distinguished Lectures. Tonight's a distinguished lecture. Yes, it says Space 2050. I had to make sure. The future of space activities. Dr. Nelson Perdero is the Vice President of Advanced Technology Center at Lockheed Martin Space. In this role, he is responsible for leading an organization of approximately 500 scientists and engineers in advancing space science and technology. His organization's mission is to create novel capabilities for our nation and customers and technology for Lockheed Martin. Pursuing that goal, Dr. Perdero leads a world-class team across its rich technical portfolio to deliver impactful innovation and growing that organization's capabilities and reputations as a research and development center of excellence. His organization has broad expertise, including space sciences and instrumentation and phenomenology and sensors, optics and electro-optics, telecommunications and photonics, guidance, navigation and control, modeling and simulation, information systems, thermal sciences, materials, and nanotechnology, and there's probably a few more hidden back there someplace. Since joining Lockheed Martin in 1996 as a research scientist, Dr. Perdero has progressed through technical and organizational leadership roles. Prior to his current role, he was the chief engineer for the Strategic Missile and Defense line of business, leading a collaborative team of cross-functional engineers across all programs focused on designing, developing, integrating, and delivering flight missile systems across the suite of programs. In that role, he is engaged in architecture definition, technology development, and technical trains for systems that include strategic missiles, advanced interceptors, directed energy, and hypersonic systems. Prior to that role, Dr. Perdero was the Science and Technology Director at the ATC, with responsibilities for the technology development and transition into space products. Dr. Perdero has a PhD in aeronautics and astronautics from Stanford University and a bachelor's and master's degree from right here at ITA in Brazil. So please join in welcoming him home to ITA.
Good evening, James. Thank you for the kind introduction. I really appreciate that. So about a year ago, when Pascal Effenhardt, who's the president of COSPAR, asked me if I wanted to come and talk to the ISU, I said yes right away. I was very excited about that because what I'm going to be talking to you about here today is something that I started about 1.5 to 2 years ago with my team at Lockheed, and it's about envisioning the future of space. So, as James indicated, I'm the Vice President for the Advanced Technology Center, which is the R&D labs or the innovation labs for Lockheed Martin Space. We're headquarters in Silicon Valley, in Palo Alto, heart of Silicon Valley. We've been there for over 65 years. If you come to visit, I always show that to visitors. We have an aerial picture of our facility and looking more broadly around. And it's really the Lockheed Martin Advanced Technology Center at Stanford University. And there's no HP, which is now Tesla, just next door to us. There's no Xerox PARC. We're really anchor tenants starting Silicon Valley in high technology. Over the 65 years, we have focused on developing new technologies and capabilities that enable space systems. So when we look at the history of the organization and everything we've done, almost everything is the first time, right? The first reconnaissance satellite, Corona. The first submarine launched intercontinental ballistic missile, fleet of FBM. Those are all things that came out of that organization. But this is about the past, and I'm here really to talk to you about the future. And you might ask, right, who in their right mind would be trying to predict the future 30 years ahead? Space 2050. And why 2050? So let me just say a few words about that. So there is some arbitrariness in choosing 2050, but there's also some thought behind it. I chose 2050 because it's far enough into the future that we have time to really develop, really create, really invent, really demonstrate breakthrough technologies. And through this conversation that we're going to have today, I will be sharing some of that with you. But it's not too far out, right? It's not 2100, 2200, that it becomes a science fiction exercise. So far enough out that you can really do it, and you can do things that are remarkable, not too far that it becomes unreasonable and a dream. So that's the story behind 2050. Now, why would we want to do that, right? I'm an engineer. Most of the 500 people on my team are scientists, physicists, engineers. And I got to tell you, this whole exercise, this whole project, Space 2050, was very uncomfortable. People are very uncomfortable with that. And the reason is that as engineers, we are very comfortable and we're used to given a problem that is well-defined, and then you go solve it. It may be a difficult problem. It may take many years to solve, but you can frame it and you can work on it. Thinking about the future and envisioning the future is a very different kind of exercise, right? And this group of engineers and scientists were very uncomfortable with that. So my conversation with the team is first to make a distinction between predicting the future and envisioning the future, right? I said, do not worry about the fact that we're probably going to get quite a bit of this wrong, right? As we try to envision the future, maybe 50%, maybe 75%, maybe more wrong, right? But that's not the point. The point is really to envision, and there is a nuance here between prediction and envisioning, is envisioning the future far out, envisioning different scenarios, how this future could play out, and then finding common threads. And what we uncovered as we went through this uncomfortable exercise, that there are some common threads. There are some common capabilities, some core capabilities that even if you look at different scenarios, there's actually very little doubt that you're going to need that, right? So think about truly reliable, unbreakable communications, right? That have bandwidth that is 10 to 100x more than what we have today. Well, that's almost like infrastructure. Every mission we do, you need communications. And if anything is happening, trends over the years and looking ahead, the data, the amount of data that you need to communicate, the amount of communication you need is increasing exponentially. So that's certainly something that you're going to need to work on. Okay, how do you go about that? That's a different story, right? That comes after you decide that this is a capability we need to have. This is a capability we need to augment, and then you go look at how to do that, right? Think about on-orbit assembly and repair, maybe even on-orbit manufacturing. Very little doubt that we're going to need those kind of capabilities. Think about nuclear power and propulsion. Very little doubt we're going to need about that. So we went through this exercise and we identified a number of these core areas that fundamentally we want to start investing on now, because they will take sometimes 5, 10, 20, 30 years to develop. But if we don't start now, we will not have those capabilities 50 years from now. So that's the balance here behind 2050, and that's the balance of why we do it. So I don't expect you to be familiar with Lockheed Martin. Lockheed Martin is known as the largest defense contractor in the world. We see ourselves as a security company, a global security company. We've been in existence for over 100 years. And our mission, if you look in the past, and if you look at what we're doing in our portfolio, and if you look at what we're shaping for the future, and I'll share some of that here with you, really, those missions, those activities fall in 3 buckets, right? Our mission is to protect, our mission is to connect, and our mission is to explore, right? And so as I mentioned today, I want to share with you, I'll start by sharing with you this vision for the future that we have. And then after that, I'm going to be sharing with you examples in different mission areas of technologies and capabilities that we're working on right now. So bear with me, because I'm not going to be showing you something that is finished, prepackaged and ready to sell, right, or ready to use. I'm going to be showing you work in progress. And I'm going to be showing you where we are on that and the challenges that are still ahead. Okay? But before we start on that journey to the future, I want to share a little movie here, a little video with you, just to get us warmed up to the conversation.
Our purpose is found in the why of exploring what lies beyond.
InSight has passed through peak deceleration. Altitude convergence, lander separation commanded. Altitude 600 meters. Altitude 400 meters. 200 meters. 80 meters. 60 meters. 30 meters. 17 meters, standing by for touchdown. Touchdown confirmed.
NASA's InSight lander has measured the first ever Mars quake inside the red planet.
OSIRIS-REx completed a daring 2-year mission, studying and collecting a pristine sample from the asteroid Bennu. Scientists are hoping to discover insight into the origin of our solar system.
Our why inspires us to protect, connect, and explore, today and for generations to come.
It's really something else. I can't believe we're here.
Unearthed long ago, the why is what gives us our purpose. A mission to advance the human race into the dawn of a new space age.
Mars Base Camp, this is Lunar Control. You are a go. You're cleared to proceed to Mars. Go make history.
All right. So I've been in this business for many, many years, and this still gives me goosebumps. Even though I've seen this movie, I don't know, 10 times, 20 times, right? So hopefully you feel the same way. We're all passionate about space, and we're all on this journey together, right, to bring humanity beyond Earth. So let's talk about the future. Let me just make a couple comments here on this. So we start with Mars, right, and we're very proud to have been partners with NASA in every single NASA mission to Mars, and now planning to go back for the Mars Return Sample mission. You also saw a little bit of a movie here about OSIRIS-REx, right? The NASA mission, we built that mission for NASA also, that rendezvous with the Bennu asteroid. Bennu is about, I don't know, maybe half a mile in diameter. The rendezvous occurred and the sample collection occurred at about 230 million miles from Earth. That's really far, right? Even hard to imagine. You can imagine the degree of autonomy that you need to have on that spacecraft and degree of accuracy in terms of the orbits. And then when you get near the spacecraft, you need to do this proximity operation, right? This rendezvous maneuver to touch the asteroid and collect the samples. So the sample collection happened about a couple of years ago. It was very successful. The sample was going to arrive in the fall, so it's a few months from now. So we're very excited about that. What's not so well known is that the technology that was used to do that sample collection maneuver, to look at the asteroid, figure out how far the spacecraft is, how fast it's approaching the asteroid, what is the relative attitude, and then correct the thrusters to do the successful sample maneuver. That was developed at our labs about 10 years ago. That's the kind of time frame for some of these, for some of these technologies. When I was there as a scientist developing the technology at the time, and I can tell at that time, we were not thinking of an asteroid. We were thinking of a rendezvous maneuver with a spacecraft, one that potentially went inoperable, but wasn't designed for proximity operation, rendezvous and docking that you want to repair. So we invented this technology. It did what it needed to do. And then a few years later, when we're developing a system for NASA, and the baseline sensor, which was a LiDAR sensor, proved to be inadequate because it didn't provide a map of the asteroid. It didn't provide situational awareness. And the asteroid is very rocky, with boulders the size of the White House, so you could crash a spacecraft. We then adapted this technology to enable the mission, so very, very successful mission there. Okay, well, let's talk about the future. And another interesting topic is when I started this exercise with my team, we all wanted to talk about the right top side here of this picture, right? We all started talking about, okay, what are the missions in space 30 years from now, and so on and so forth. And we paused and said, well, you know what? Let's spend a few minutes, just a few minutes, talking about what's happening on Earth 30 years from now. How do we gain access to space 30 years from now? Because the time frame, again, right, 30 years, 28 years is far enough that you really can look at different ways of doing things. And what happens on Earth and how we get to space has tremendous implication to what you can do in space. So I'll just spend a few minutes on that. And then I promise we're going to talk about the right side, the rest of the whole talk. So what do we envision in this kind of time frame on Earth is a whole new level of integration in the models and analysis tools, right? As James indicated, I went to school at ITA, and then after that, I started working in engineering. And I remember at that time, you know, if I wanted to do an analysis of a space telescope, right, I do the mechanical modeling, then we generate the finite element model, we do the structure analysis, then you do a finite differences model, right, and you go do your thermal analysis. And then you tie all that together with a control system that shows you how well you can point to your stars or so, or wherever you want to look at with your telescope, and your jitter, how much it's vibrating, and so on. And then you tie that up with an optical model, right? And it was very manual, very laborious, right? We have come a long way, right? This is 25, 30 years ago. We have come a long way. Models have been greatly integrated. The interfaces are easier, right, to translate one model to the other. But we have a long way to go. And in 28 years from now, 27 years from now, there will be a whole level of integration where even the space professionals like us, right, we're going to be able to talk about high-level mission requirements. And we talk about ChatGPT, right, it generates a letter for you and so on and so forth, and the equivalent of that, right, and engineering GPT or whatever it's going to be called. We'll translate that and feed that into fully integrated models that does the design for you. And imagine that this capability now, we train it so that it can leverage the knowledge from decades of superb, brilliant engineering that happened at NASA, ESA, JAXA, you name it, right? At companies. And you can train it, you can have best practices, and that can all be embedded in these tools. These tools will be highly integrated. What happens when you do that is that your design phase, right, is greatly compressed. Okay, you can do that very fast. So that's one element, but that's not enough. We also need to be able to prototype and bring high levels of automation to prototype and to demonstrate some of these new designs. So we have come a long way from the point of view of manufacturing, producing spacecraft. To my knowledge, the first spacecraft that you could say was mass-produced was Iridium, where we built about close to 70 spacecraft. Lockheed built that a few decades ago for Motorola. It wasn't commercially successful, but from the point of view of engineering, it was very successful. Today, we are already at a new level, right, with Starlink and some other systems that are being proposed where you're building tens of spacecraft a week, right? And you're building basically to a particular design. When I talk about automating the prototyping is, yeah, you're doing the mass production, but not just building them all the same, right? You can vary that. So you're going to be able to automate the prototyping to demonstrate some concepts, and you're going to be able to take this mass production that we have today to a new level where you can now tailor. Not every spacecraft coming out of the line are exactly the same. Think about technologies like when you're integrating these vehicles, that is like, think about a no harness integration, right? There is no harness, everything is wireless in the spacecraft. Things like that. So we call that one-click design. When you put together the integrated design piece, development up front, the integrated prototyping, and the mass production at the end. One-click design. When you have that, you totally change the equation on how we think about developing space systems. You invert the curve of non-recurring engineering, right? There's basically your effort and time and money that you spend to do the design, and then you have to change, and you spend another amount on top of that, right? You totally change that. And then the recurring, there's the producing piece. You invert that curve. And what that's going to allow us to do, that will mean that the speed of innovation is only limited by the speed of ideas. So we, the space community, are going to spend much more time thinking about what missions we need to be doing, where we need to be focusing on, what data we need to be measuring, and so on. And this automation will help us through the design process. We'll shorten the time cycles for that. We'll demonstrate the rapid automated prototyping and then mass production. And if you're mass producing spacecraft and they're coming now on a cadence, now you need a way to get them to orbit. And I, on purpose, I'm using words like access to space as opposed to launch, right? We have seen a lot of progress in launch in terms of reduction of launch costs. In this kind of time frame, we see that continuing, especially with the use of new business models where you could almost think of a no-cost launch because the entity or the company or the concern bringing together these assets to space, make some sort of partnership with the launch company that the business model allows them to deliver these assets to orbit for free and then recoup their investment or their launch costs later, right? So that's one piece with the business model and continue on the launch part. So when we talk about innovation, it's not only technology, right? Innovation in business models and innovation processes, how we do things. But if you're talking 27 years from now, right, 2050, we should also be thinking about revolutionary ways to gaining access to space. And I put the picture here of a space elevator to be provocative, but it's not unreasonable, right? If you really look into it, the concept of a space elevator has been published for decades. It doesn't violate any laws of physics. It is a real difficult engineering and materials problem, right? But if we put our minds to it as a community, we can make it work. And then just think a moment, right? Just think for a moment that, let's say we do get a space elevator to work. Maybe we start on the moon, not on Earth. That really changes the whole thing, because right now when we design space systems, they're designed to survive the launch loads. And then they operate on what is a fairly benign environment, right? I mean, it's harsh from the point of view of radiation. It's hard from the point of view of thermal swings. But from the point of view of mechanical vibration and so on, it's a very benign kind of environment. That makes it really, really difficult to, we end up having designs that are driven by those launch loads, right? Especially when we're talking about precision optical systems and things of that sort. That totally changes the equation, because now you have a smooth ride. So just think about that. And there are other technologies such as a spin launch and so on that we need to look at if we're thinking about this kind of time frames. Also, when I talk about access, normally we talk about, when we think about orbits, we talk about LEO, MEO, and GEO in this kind of time frame, and we're already seeing it now, a geographic expansion of our use of space into cislunar. And that will present a lot of challenges associated with that. And also a political expansion where every country on Earth will have an interest in space, either by designing, producing, launching, and operating their own spacecraft, or acquiring assets that they operate from others. So an expansion in general in terms of our access to space. And then finally we get to space, and that's where I'm going to spend most of the presentation. But let me make some remarks here. When we look this far out, and we are already seeing some of these trends today, the example I gave early, and I want to put that all under the umbrella of infrastructure, right? For the space economy really to thrive and flourish, we need to have infrastructure that these new companies, new entities can tap into instead of having to develop everything themselves, right? So we start with communications. Think about truly secure, unbreakable communications that provides you 10 to 100 times higher information content or bandwidth than what we have today. We're going to need that. We are already seeing mega constellations being launched. We see a trend on that to increase. This is going to get congested, right? The spectrum is going to get congested. So how do we solve that? I'll be sharing an example with you of a technology that we're working that, provides a potential solution for that. I talked about on orbit manufacturing, repair, and assembly, and that's going to make a lot of sense. There's a lot of conversation already in terms of if we can truly utilize the regolith on the moon or Mars, does it make sense to produce some of these assets, solar arrays or so on the moon, right? And then you launch from the moon where the gravity well is so much weaker than the Earth's. So really very, very different concepts. Nuclear power and propulsion. Think about infrastructure. Power, we can't do anything without power, right? So power and propulsion. Different ways to utilize power, right? Where you could have centralized power units that do power beaming to a number of different assets, simplifying the different spacecraft and different assets they're designed, right? Because you don't need solar arrays and so on and so forth. We're seeing space getting congested and contested, as we talked about. We see the problem of space debris. So there are whole new mission areas that are going to be needed. And there are also opportunities, right? So how do you do space debris remediation? How do you do space traffic management? How do we automate? How do you automate the system so that they can do automatic collision avoidance and things of that sort? So a whole new scenario here for space. And I'm going to be talking about different mission areas with you, and again, sharing some of the work that we're doing to enable some of these technologies. So, starting with remote sensing. A lot of what we do from space is looking at the Earth and figure out what's happening. And in this time frame, we're going to be able to monitor the entire Earth continuously, right? We're going to be able to track every object on Earth if we wish to do so. And so the picture here is interesting because what are these little pancake objects on the screen, right, that don't have solar rays and so on? Well, I already kind of gave you a hint on that, right? If you have a nuclear power unit generating power in space that can beam power to your spacecraft can be greatly simplified. You don't need those appendages and so on and so forth. Well, but this is a very different form factor also, right? With since the time of Galileo, when we talk about, if you're observing in the visible domain or IR with a telescope, you have a primary mirror, you have a secondary mirror. So you don't see any of that here. You see basically a fish eye. So there is a technology that we're developing called interferometric imaging that will enable that. And I'll be talking about that in the next chart. So these are very different concepts where you're going to have all these systems networked in space. You're going to be able to monitor every element on Earth. And you're also going to be able to have situational awareness. You're going to have to monitor every object in space also. With space getting congested with more and more assets, that problem becomes exponentially more difficult. And with us expanding into cislunar, that becomes geometrically more difficult. So, first technology I want to share with you, I like to call it imaging computer. And as I mentioned, since the time of Galileo, the way we do imaging is that we collect the light, generally on a primary mirror or lens. We focus that on a secondary, tertiary, and finally on a focal plane. So that's imaging on the focal plane. It works very well. This is not going to replace it for every mission, but it will replace it for many missions. What we're talking about here is doing interferometric imaging. So this technology, right, interferometry, has been used in radio astronomy for many, many years, has been used in optical imaging over the past couple decades or so, generally with a small number of large telescopes that you can change the baseline, generate interferograms, and then calculate an image out of that. What we're talking about here is really taking this interferometric imaging in a whole new direction, at least in 2 dimensions, right? We're talking about a solid-state array with thousands of lenslets that collect light into a photonic integrated circuit that then combines those lights from those different lenslets, thousands of combinations, generating thousands of interferograms from which you can calculate an image. So this is called interferometric imaging, computing imaging. We've demonstrated that through analysis. We've demonstrated that in the lab. Why would you want to do it? Number one order of magnitude reduction in mass and volume of your space telescope, right? That alone justifies it. Number two, that's not so obvious, is that it totally changes the way you develop and you do integration and test of these systems. If you ever work on the development of an optical telescope for space, it is very complicated at the end in the manufacturing of the optics and so on, but it's also very complicated through your integration and test, the alignment of the optics, all the tests you need to do there. This is not simple, but what this does is it shifts the complexity to early in the design and development phase and brings the complexity to a very controlled environment, because these devices that I mentioned to you, these photonic integrated circuits, these are basically built in a semiconductor factory. These are solid-state devices. They're complex. But once you have the factory lined up and you build them, you can manufacture them on a cadence. You can mass produce them, and they're very robust. So it totally simplifies your integration and test of your entire system later on. We're very excited about this technology. The next technology I want to share with you, we call that disturbance-free payload, and that's for ultra-stable platforms. So if you work on an optical system, the optics are very important, but that's not enough, right? If you have perfect optics, but if your system vibrates or if it doesn't point in the right direction, you're not going to get good resolution, you're not going to get good accuracy, and so on and so forth. So precision pointing of optical payloads is extremely important. Precision pointing for laser communications is extremely important. So this system here is what I like to call close proximity information flying. How close? A few millimeters. The idea here is to physically separate your payload from your spacecraft. So imagine you cut You make a physical cut and you mechanically separate the payload from the spacecraft, and then you couple them using non-contact actuators, such as voice coil actuators, similar to the ones you have in your speaker in your house, right, in your sound system, except that they are specially designed. They have large gaps, a few millimeter gaps, so they can move with respect to each other without contact, and you can apply forces between them without contact. You also, on that interface, you use non-contact position sensors, optical, capacitive, inductive, several technologies exist for that. The picture you're seeing here is a picture in one of my labs. You'll see two colleagues of mine in the lab. We put a black background just to make it nice and not a messy lab. But what happens here is that the payload that I showed you on the right side here, it's hanging from the ceiling on a cable. So in 1G, you got to deal with gravity. So that's the way we did it. It allows it 5 degrees of freedom, right? You can swing in 2 directions, and then you can rotate around the cable stiffness. And then the spacecraft on the other side is hung on a separate cable. And we've demonstrated that over 60 dB broadband isolation down to 0 frequency. So the pictures you're seeing here on the right, the animation is what kind of wavefront error, how pristine is your wavefront from an optical system using state-of-the-art vibration isolation system on the top, and what you get with this kind of approach, right? It's an architectural change on the way you design your system. So over 3 orders of magnitude improvement in vibration isolation. So we're very excited about that. Now, if you tie this up with the 2 pictures I showed you on the prior chart with those pancakes, right? You can imagine now you can bring these pancakes together and you can couple them using this kind of actuation, non-contact actuation. You can have a very large aperture by assembling these systems in space, if you will. So a lot of opportunities by bringing these 2 technologies together. Let me change topics and talk about communications, and this is one of the areas that I'm most excited about. As I mentioned to you, we are already seeing the proliferation of mega constellations. The trend there is to continue, right? The demand on bandwidth, the demand on the spectrum is only going to increase. How do we mitigate that, right? The other aspect of this is if we really want to rely on communications as a basic infrastructure, it needs to be trustworthy. It needs to be unbreakable, right? So that brings us to quantum communication, quantum key, this distribution. And there are many demonstrations that have been done of quantum key, this distribution for communications, basically in the laboratory. Unfortunately, to date, none of these demonstrations really scale to bandwidths that really are conducive to an operational system. In the next chart, I'll be showing you an architecture where we do have something that not only scales to bandwidth required by operational system, but we're expecting a 10 times increase in information content. I'll be talking a little bit more about that. So think about, again, laser communications, this network of spacecraft. Think about a system where, because the communications need to be unbreakable, and need to be secure, need to be reliable. Think about a mega constellation with thousands of spacecraft where you can lose 1, you can lose 2, you can lose 10, you can lose 20. And the degradation performance is graceful, right? It doesn't really stop working, it degrades the performance graciously. So in 2015, I attended the Goddard Symposium, and I made a presentation, and I used the term disposable spacecraft. And there were a lot of eyebrows raised, right? But if you now start to connect the dots from this conversation we're having here, and you think that we can really do one-click design, you can really automate your prototyping and your mass production, you have access low cost to space, you can imagine that you're going to be replenishing these mega constellations on a cadence. And so if you lose a spacecraft, 10, maybe even 100, that's part of the cost of doing business. And the concept of a disposable spacecraft really doesn't become unreasonable, right? So this is what we're thinking about in terms of communications, right? Basically a backbone, mesh networks that when you design your new system, when a new company designs their own system, they can just tap into, right? They don't need to go develop that whole infrastructure themselves. So I wanted to talk about quantum communication because this is, of all the things I'm going to talk to you here today, this is the one that I'm most excited about, right? Our team has come up with an architecture that truly scales to operational bandwidths that are required for operational systems and promises a 10-fold to 100-fold increase in information content. So think about number of bits per photon, right? So how do we do that, right? What is the approach we're taking? There are basically three fundamental breakthroughs that allow that to happen. The first one has to do with the protocols and with encoding information. The team is using multitasking or multiplexing spatially, in the time domain, and spectrally. So 3 levels of multiplexing to really increase information content. We've demonstrated that in the field. The second breakthrough is the use of exploring the phenomena of superposition, right, or the duality in quantum systems. And what that allows us to do is to really beat the noise floor, to significantly reduce the noise floor in the detectors. So you can have detectors for your communication systems or for your remote sensing systems that are an order of magnitude or more sensitive than detectors that we have today. And the picture here on the center, the picture here on the center is of a single photon Geiger mode detector that can do just that. The picture on the left is the example of the spatial multiplexing using a thin film optics to do that. And the picture on the right is really a demonstration of the system in space. So I told you about the 2 first breakthroughs. The third breakthrough has to do with the light sources, right? And basically what's called bright light sources that are enabled by investments by DARPA primarily on waveguides that are nearly perfect. So you put these 3 elements together: bright light sources, exploring the duality in quantum to beat the noise floor, and then you're encoding by multiplexing in 3 different domains, and you have systems that can really increase the information content per photon. We've demonstrated that in the field, not in space, but in the field we've demonstrated that. We demonstrated quantum communications in sunlight, not just in the dark. And we are on a path to demonstrate this for space, and we're going to need this if we are to realize the vision that I shared with you on the prior chart. The next example I want to share with you, we call it electronics for Mars, right? So for many years, we have very successfully developed electronics for space. Some of our systems have had decades of operation in space. They are, though, very costly, right? They require dual, sometimes triple redundancy. They require a lot of shielding. They require a lot of radiating of the electronics itself. So as we see the electronics and advances progressing, right, with GPUs and so on, how do you bring those out to space without having to incur this enormous cost of time and money to make them reliable and operational in the harsh environment of space? So there are several approaches for that, and we are working, for example, with NVIDIA, and we're bringing some special shielding and some novel 3D printing techniques of materials that have good radiation hardness properties and so on. So that's one approach. We'll continue to do that. The approach that I'm suggesting here on this chart is a little different, right? And it's not one or the other. It's something that we need to do in parallel. Because if we have enough time, and if we're thinking 2050, we can rethink the way we build electronics. So the idea here is to build electronics that are carbon nanotube based. Why would you want to do that? Well, carbon nanotube based are inherently radiation resistant. They are non-volatile, and they can be packed in 3 dimensions, so for very high density memory devices and electronic devices. The picture on the left is a memory device that we flew and demonstrated in space that worked well. The picture on the center are logic devices that are carbon nanotube based, so these are field effect transistors. We use similar manufacturing techniques than those used for the semiconductor industry. These have high electromobility, and these we have not flown yet, but we have demonstrated in the lab. So if you have the memory, if you have the logic, you can now start thinking about an electronics that is entirely carbon nanotube based, that is inherently radiation tolerant, and that's why we call it electronics for space or electronics for Mars, because it's a whole different way of approaching this problem. Let's talk about defense. Unfortunately, all you need to do is to look at the news every day, and there is some conflict in the world, there is some unannounced missile launch and so on, and even though I think we all would like to think that this is going away in 30 years, chances are it might not. So we need to be relentless about developing technologies that provide for defense, right? For example, missile defense technologies. And as I talked about the proliferation that we're seeing in space, there's also, unfortunately, proliferation in terms of missile launch capabilities and so on. So it will be more challenging to be able to track our assets in space, to be able to track our missile launches, and so on and so forth. And it will be more challenging, but it will also be very necessary, as it is even more so than it is today. So the technologies that are going to help us to do that is basically our ability to detect and track those. So the challenge is going to be increased just by the sheer numbers and the sophistication of some of these devices, some of these threats. But we're going to be able to mitigate that by using some of the sensor technologies that I mentioned to you in the prior charts, like interferometric imaging, quantum remote sensing, and so on. These are sensors that are way more sensitive. And then if we really remember what I mentioned, that we are going to be able to monitor the entire Earth all the time. And if you bring now advances in algorithms and AI, machine learning, and so on, to really stitch all that together and extract information, that's going to help us to monitor and defeat this threat. So the first technology area that I want to talk to you about is what James asked me about, phenomenology. Really, what does that mean? So that's an interesting term. It comes from phenomena. Phenomenology then is the area where you're trying to understand the phenomena, the nature of phenomena. So what we're trying to do here is really answering the questions. What does nature allow us to observe, right? So depending on what you're trying to do, if you're doing an astrophysics mission, right, you're looking at the deep space and you're trying to find the origins of the universe. What are you looking at? What is the spectrum? What are the bandwidths? What are the orbits? What's the environment? What is the transmissibility between what you're looking at and your sensor? If you're looking at a missile, right? What is the chemistry of that missile? What's coming out of the exhaust pipe? How can you track that? What is the phenomena you wanna understand? So that's what phenomenology means. We have a long history in that area, going back 60 years from the creation of the organization. We have a group that's really good at that. It's a group of physicists, chemists, and so on that really can understand that. What's interesting on this area and what's really changing, especially in the past 5-7 years, is the combination of fundamental first principles understanding that we have done now for several decades, right? I talked to you about understanding the phenomena from first principles. With the combination with the advances in machine learning and AI, putting these together and bringing different modalities, right? Optical, infrared, multispectral, RF, bringing all these together, what we're finding is that these new algorithms, these new techniques, right, the deep learning, are allowing us to detect new patterns when you bring this together that were not obvious, even though we had that fundamental first principle understanding before. So tremendous advances in those areas. And it starts here, right? If you cannot detect, if you cannot track, if you cannot understand what's happening, then there's very little chance that you can do something about it. The second technology I wanted to talk to you about is directed energy. So for several years now, we have done a lot of work in directed energy, basically related to missile defense, right? So we've been very successful at basically hitting a bullet with a bullet. So that's a kinetic intercept, right? If somebody launches a missile at you, you intercept it with another missile, right? So we have developed a theater high altitude area defense system and a number of other missiles that have proven to be very successful. Directed energy is a way to augment that, not to replace it, right? And if you have a missile coming at you or a drone, right? We're seeing proliferation of drones. Unfortunately, there are some organizations, some individuals that are using, putting armaments or a grenade or an explosive on drones and, creating harm. So how do you defend against that? Directed energy is one element that can be very effective on that. Now, the reason I have directed energy here is I'm just sharing with you the work we've done on that would be very successful. But the reason I have it here is because a lot of these technologies play a very key role on a power infrastructure for space. You heard me talk earlier about if you have a nuclear power generation in space and you can do power beaming to different assets, that's a very elegant and interesting way to provide a power infrastructure, right? Without having to lay out cables and a more extensive physical infrastructure for that. So a lot of the technology that we develop here to do this directed energy, they translate to power beaming. So that's why it's very relevant here. And in fact, we are already using that. We already have contracts with NASA and DARPA to do exactly that, to do power beaming and study how power beaming can enable some of these future exploration of space. And talking about exploration for space, hopefully you're familiar with NASA roadmap, NASA Gateway, and so on, that really starts with the moon and using the moon so that we can learn on how we're going to explore Mars, right? Space is a very harsh environment, as you know. So our vision for space, and there are different visions for space, right? There are visions with thousands of people in space, there are visions with thousands of people on Mars, and so on in this kind of time frame, maybe even sooner. Our vision is slightly different. We envision an exploration of space that is really more of a combination of human and robotic exploration of space, right? Because when you're bringing humans to space, it adds a lot of complexity, it also adds a lot of costs. It also adds a lot of value. So what we see is trying to do both. So think about telepresence, think about technologies for collaborative task execution between humans and a team of humans and robots. That's what really envision for space. And we envision a continuous presence of robots on the moon and Mars, and a rotatory presence of humans, right? With humans expanding a certain amount of time and then rotating out and another team coming up. A big problem here is even medical technology, right? We need to be investing in medical technology for DNA repair technology because of the radiation environment. And then radiation shielding so that you can keep humans in space for extended periods of time in a safe manner. So in situ resource utilization so that you can build on the moon, as shown here. On the left, the bottom left here, we have a nuclear power generation. Then you see the power beaming that I talked about. Lunar mobility, I'll be giving an example of that coming up. Lunar communications. Lunar positioning system, right? Equivalent to our geopositioning system. So LPS. In addition to lunar, we also see as enabling for this expansion into space, not only Moon and Mars, but also the whole cislunar aspect that I mentioned to you. We're going to have depots in space. That picture on the top left shows a depot of cryopropellants. The element on the right is, again, a nuclear power generation, a power distribution system, sending power to elements on the moon, sending power to the cryo depot, and sending power to other spacecraft. And then you see the analog of that when we go explore Mars. So what are we doing in that area? A few things. So on-orbit services, as the space economy grows and more companies start going into space, having standardized interfaces is a key element for that. Not only standardized interfaces so that you can do automated rendezvous and docking to do repair, but to do also the refueling for some of the spacecraft. The picture on the top left is the natural feature tracking that I talked to you. And those pictures I actually found the charts about 10 years ago when we started that project to do automated rendezvous and docking and repair of an operable spacecraft that we later adopted to do the mission with the asteroid, with Bennu asteroid. So think about this, right? Of course, we want to standardize, we want to have fiducials and so on. But in parallel with that, we can also develop very robust systems that, like this natural feature tracking system, that you could approach an object that either wasn't designed to do proximity operations, rendezvous and docking, or it's inoperable. And you can, by imaging it, you can create a solid model of that. You can find fiducials and so on. You can do proximity operations, and you can do automated rendezvous and docking if necessary with those. You can think about doing that in space. You can think about doing that on the surface of the moon, on the surface of Mars, or surface of other planetary bodies that we're going to explore. The picture here on the right is another augmentation system. This one we're developing ourselves. The one on the left is by Orbit Fab that we're partnered with. The one on the right also allows for hardware augmentation, right? You can attach a new computer system and increase your computing power on the spacecraft. So there's a lot of these interfaces being proliferated. And the question now becomes, as a community, right, what are we going to standardize around, right? It doesn't need to be a single one, but it needs to be a few so that we're not doing, we're not developing systems that are totally disparate and not consistent with each other. compatible with each other. We have partnered with General Motors on an effort that we call the Lunar Mobility Vehicle. So, of course, with NASA and General Motors in the past, we've been on the moon. We successfully developed lunar rovers. These are very different rovers. These are being designed and developed for fully autonomous operations. They can also be driven and operated by an astronaut, but they don't need to. They're also being designed for very long lives, right? Because we want to go to the moon to stay. And the concept here, remember, I talked to you about innovation in terms of technology, but also talked about innovation in terms of business models. So imagine if different companies that want to have a presence or explore the moon, if they have to develop their own rover. I mean, that's a non-starter, right? That's going to diminish the speed with which we advance this space exploration by, I don't know, 3 orders of magnitude or more. So what we're thinking about here is a service, right? A lunar mobility vehicle. So if a new company has a plan and so on, they can rent the rover services for maybe a week or so. And we can pre-position the rover. The rover has robotic arms. It can move material. It can move parts and so on and so forth. And it can support, basically a lunar ecosystem, if you will. Well, to be able to do that, you need to communicate and you need to navigate, right? So another services, if you will, model, another business model here is the system that we're calling Parsec. And Parsec will start with 2 spacecraft that are going to be orbiting the moon. And they provide communications amongst different points on the moon and also communication between the moon and Earth. And they also provide lunar navigation systems. So if you want to pre-position, you know where you need to go and so on. So those provide the services. In future years, we're going to be deploying further spacecraft to augment the constellation. So I talked about a lot about low Earth orbit systems, remote sensing, looking at the Earth, communication systems for the Earth. Maybe I went as far as the moon, but a lot of what we do, we have a long history of work in NASA, is deep space exploration, right? So I did talk about OSIRIS-REx. That's classified as deep space exploration. We also built the near-infrared camera from James Webb Space Telescope. So that first image from James Webb came from an instrument that we built in my lab. Very proud of that. We have a long history of that. And as we look into, we continue and deepen this search for life in the universe, one mission that has really gotten a lot of the scientists' attention and traction is to go explore Jupiter's moon, Europa. This moon, we believe there is a liquid ocean under an ice covering, and we want to go explore and collect a sample and do some tests on that. It's a very complex mission, as you can imagine. And going to Bennu, we learn a lot of things, right? So the first thing we learn is that as we started studying that meteor, we learned that the surface is not really what we expected. It was much more irregular than what we expected. That forced us to change the sensor for navigation, as I described to you. The other piece that's not so unknown is this arm on the OSIRIS-REx spacecraft. It's called TAG-SAM, for Touch and Go Sample Collection Mission. Was also developed in my labs. It's about 2 meters long. When it touched the asteroid, it actually went 2 feet into the asteroid. So the surface of the asteroid was very soft. We didn't know that. Well, this could have crashed the mission. We could have ended the mission right there. Fortunately, we had enough gain in phase margin in the control system of the spacecraft that it pulled away and it collected a sample and everything was okay. Now imagine, now we're going to go explore Europa, right? And the ice covering and the liquid ocean under there. It is not unreasonable to think that there are going to be a lot of unknown unknowns, right? So what we need to do really is not rely solely on understanding and predicting every possible circumstance. Right? We should definitely try that, but not only that. So what we're doing is developing systems that are more robust and they can learn as we do when you encounter a new problem, when you encounter a new situation, when you encounter a new environment, right? So what we have here is something we call causal and reinforcement learning. And this is basically a model that is running on the processor on the spacecraft. It has a model of the environment, but it's a model that evolves. It has a vision model, so it has a number of cameras in different wavebands that monitor the system. It has a memory model, and it has a structural causal model so that it can take all these inputs from the environment, and when it encounters an unknown situation, it can reason as opposed to just shutting down, sending message to Earth and asking, what do I do next? I mean, on Europa, just the travel time is extremely long. It would not be feasible to do something like that. So we're working with JPL in this area. So really bringing automation through the use of AI and machine learning to a new level, right? Level 3 AI and so on is a very key enabling technology for future exploration. A lot of systems that we already have in orbit provide an enormous amount of data that gives us information about the Earth. And today, we're not really taking full advantage of that, right? So in this kind of time frame, we're seeing this is starting now. I'll share an example with you. We call this, helping Earth or improving life on Earth in a more systematic manner. How can we use the systems we already have, the information they already provide, right, to do disaster assessment, disaster monitoring, disaster response in a more effective manner than we do today? How can we use the systems to enable not only smart cities, but smart worlds and so on? There's been a lot of progress in that area. There will be another quantum leap. And then what systems should we be designing and deploying that are truly geared at improving life on Earth, improving our stewardship of the environment, right? That we are feeling global warming, or feeling all these changes that are affecting us. So let me give an example here. We call it GeoHealth. On the left, I have a picture from one of the instruments we built. It's called GLM, Geo Lightning Mapper. It monitors lighting, intercloud lighting on Earth. It is an instrument on board of the GOES spacecraft series, which is a geostationary meteorological spacecraft by NOAA. We have 2 of those. And what the scientists found is that there is a strong correlation between the increase in intercloud lightning, the frequency of that, and the onset of tornadoes. So today, using the systems we have today, we have maybe about a 3 to 5 minute warning for tornadoes. Using this system, you're going to bring it to 30 minutes, so you're saving life and property. So that's one example of that. The example on the right really goes more to the comments that I made on the prior slide, where we do have a lot of data from our spacecraft that we can detect a fire as soon as it starts, right? And but we're not really using that. We're not tying that system with a communication system and tying that to the first responder and telling them where to go, right? This is something we can pretty much do now, right? We do have the assets in space. Now, we can go even further, right? Because we have assets that can detect when a fire starts. We have assets that can measure wind. We have assets that can measure fuel content or moisture content on vegetation and so on. So you can actually not only map your fire front, you can actually map where it's going to go. And you can pre-deploy your first responders based on that kind of information in a more predictive sense. That particular work is going on right now. We call it firefighting as a service. And today, what we're doing is tying up all this information that already exists in a more automated manner and bringing the data analytics that will provide that information to the first responder. If we think in the future, if we now pre-deploy the right instruments to really optimize for this kind of mission, we can do so much better. And this is just for fire, right? We can think of that for many other aspects of GeoHealth. And I want to finish here. This is my last chart. I want to finish where I started with Space 2050. So this is the vision we created. This is a sample of some of the technology areas that we're starting to develop now that will enable this future. But this future and this capability will not be developed by a single organization, right? In a single company. So it's really for us as a community. So I wanna finish with a call for help for all of you who are Earth citizens, but also are passionate about space, to come help us build this future. Thank you.
Okay, I think we've got a little while we can answer some questions. Have some questions. You can answer them.
If you have questions, yes, I'll be
Oh,
delighted.
I'm sure they do.
Yeah.
How you can, thank you for your presentation, very inspiring. How you can handle with the research and economic in your company? Because you need to invest in new research, at the same time you don't know if it will refund you in the same.
Right. No, that's a great question, right? And it's always interesting because it depends who you ask, right? If you ask me, right, I'm the R&D guy, we're not investing enough, right? If you ask some other executives in the company who are more on the program side, oh, we're investing too much in R&D, why are we doing that, right? This is too far out, and it is too far out, isn't it? But we have enough examples, and I shared a few with you here, right, that if you invest in the right areas, they can enable brand new missions, right? But it's hard to predict. And that's where this kind of exercise, this kind of framework, where you envision the future, and we don't do this alone, right? We started this with my team. Then I expanded that to the entire company, the entire space company. So my team is about 500 people, just to give you a sense. The entire company, we didn't talk to everybody, but it's a 20,000 people company, right? So it's much broader, right? And then we expanded that to external customers in the community, right, as part of that. And so you start, as I mentioned to you, you start to see some trends, some of these key capabilities and key technology areas that, we don't know if the future in 50 years from now is really going to pan out exactly as I described here. But some of these capabilities, there is a higher degree of certainty that you're going to need that, right? And that's actually help us guide where do we want to invest. The power beaming example I gave, right? We were investing on a number of technologies for another mission, the directed energy mission. And as we went through this exercise, power beaming became a key enabler for some of this infrastructure, right? And so on. So we actually diverted some funds to go do that, right? And now we actually have not only internally funded projects for that, we have projects funded from NASA, DARPA on that area. Yeah, hopefully, I don't know if I answered your question, but not an easy chart to navigate. Yeah.
Yeah. Okay. Thank you first for the excellent lecture on future of space activities. My question specifically on quantum communication. Mm-hmm. So I want to know what is the technology developed by Lockheed Martin to regenerate the quantum signals for long distance quantum communication, because it is still a hurdle or challenge to do a long distance quantum communication and to regenerate the quantum signals.
Yeah. So let's see. Yeah, the distance really becomes more of a challenge if you're trying to do it on Earth, right on the ground, because of atmospheric effects. In space, it's really not. It's really not inherently challenging, right? If you're doing from, I don't know, a kilometer to 100 and so on, it becomes more of an acquisition and tracking and pointing and the jitter that I talked about from a remote sensing, but we're really good at that. We know how to do that piece. The key element here in the quantum is when we think about quantum computing, and that's not really what I was talking about, right? When we think about quantum computing, that requires a large number of qubits, 1,000 or more, really, to be meaningful, and higher coherence times in generating your quantum signals, right? The architecture we came up with require very few qubits. We do not need a lot of qubits. And we're exploring through the architecture that we can take advantage of the duality of the quantum state in a very short coherent time. And we can still significantly increase the sensitivity and lower the noise level on our detectors. That's really one of the keys to the breakthrough here. The distance really is not a big player on that.
Good evening, Stéphane Bellucine from France. Thank you very much for this very inspiring presentation. I have a question regarding the strategy of Lockheed Martin, especially to achieve this time frame you have described about future of space activities. How do you balance, if you do, how do you balance between technologies and applications? In other words, is Lockheed Martin more oriented towards technologies and providing some kind of platform, for instance, for services for your customers, whether they are government or not, or more into applications, towards applications? Right. Thank you.
No, that's a great question. So I have some guiding principles for my team, right, at the R&D labs. And the first one is mission relevance. We start there, right? We're a company, right? We're applied technology. We're an R&D lab, but we focus on applied technology. So the more open fundamental research, that's really the realm of universities. And we work with a lot of universities, but they are better at that than we are. So what I asked my team to do, and you can imagine, right, we're an R&D lab. I have about 500 people on the team, and so they're very bright, right? And they have a lot of new ideas. We can't do all of them, right? So what I asked them to do is to do a thought experiment. So we came up with a new idea. So I asked them, do a thought experiment, because a thought experiment is fast and cheap. If your idea pan out, if it were to pan out, if it works, what's the impact to the mission? What's the impact to the company, right? And we use the answers to those questions to guide where we invest. So I'm giving you a little bit of a framework, but it's all about the mission. Even when we're looking far out, as I showed you here today, remember where I started, right? I started with, what are the capabilities? What is the space going to look like 27 years from now? What do we want to be doing? What do we want to be able to do in space, right? And then we use that to guide us. Okay, so what technology do we need to develop? What are the roadmaps? Okay.
Thank you for the wonderful lecture. I'm Anant from India. Actually, as my question is on the nuclear propulsion, which you just mentioned towards the beginning of your
I'm
lecture.
sorry, can you
on the nuclear propulsion.
Oh, yeah.
What is your, I would say, your view on that technology, nuclear propulsion as such, and if that technology is going to come, mainly for human missions to other planets, what would be the regulations for its operation from the Earth's atmosphere and to the planets?
Right.
And actually, one more question. In Lockheed Martin specifically, once an idea for a particular technology is conceived, how much time typically it takes towards when you finalize its requirements from conceiving an idea and finally starting to test after design? So how much time is involved in that phase?
All right.
Thank you.
Yeah, two very difficult questions. All right. So let's see. So the first one on nuclear power and propulsion. So I personally believe that is an enabling technology for the future of space, right? Now, a lot of times, and we see that with debris remediation, we see that with space traffic management control. We didn't even talk about space tourism or space mining and things like that, right? There's also the issue of policy and regulation that comes with that. But even thinking about the future and what you want to do in the technologies is good, because you start to drive those kind of questions and those kind of conversations, right? So I'm not sure how the regulation is going to play out. But for example, nuclear power and propulsion, there is a non-technical aspect to that, right? Technically, we've done it, right? We've done deep space missions that use nuclear power and so on. The other day, I had a meeting at the National Academies, and one of the scientists was describing a mission to, I think it's Pluto or so on, and it's going to take, I don't know how many years just to get there, right? And I was thinking to myself, and well, we're thinking about that because we're thinking that we're going to go and we're going to do all this orbit assist, this and that, the way we do things today. Well, what if we could have nuclear propulsion? Can we decrease that time, right? What's the sense of urgency here, right, for us to advance science, advance knowledge? Can we do that in a safe manner? I think we can. So I think we need to be pushing those envelopes and forcing those conversations. I know I didn't answer your question, right? We are doing work on nuclear power and propulsion. We're doing work with NASA on that. Others are doing work on that too. And I personally believe that that's going to be part of the solution here for us in the future. But there are all these questions about the policy and how we get comfortable, how we do it in a safe manner that I don't have answers for, right? The second question you had to do with the time lengths. So it varies a lot. What I can tell you is, and that's another conversation I have with my team frequently, is because we are the R&D lab and we're looking far out, a lot of what we're doing is technology push, meaning there is no customer saying, I need this, right? When I developed the natural feature tracking that I mentioned to you, I didn't have a customer saying we need that, right? This was, again, as the lab, as the R&D function saying, hey, we're going to need this, right? Because look, in the future, we're going to be able to, do this assembly in space, and we need to be able to map things that weren't fully designed for that, and so on and so forth. So the fastest way to accelerate development, because we can do things very fast, is to find a mission that needs that particular technology, right? Because you're pushing technology. If you find a pole, then you can bring this an order of magnitude shorter, right? So it varies a lot.
Good evening, Erez Yechezkel from Israel. Thank you for a very inspiring lecture. I wanted to ask about when trying to allocate resources in view of the 2050 vision of space. How do you decide how much to invest in commercial space technologies and how much to invest in defense technologies?
Let's see. So what I shared with you here today is the initial steps on the thought process, right? Of where do we think space is going to go, what capabilities we're going to need, right? And then we try to identify these core technologies that will enable those capabilities, right? So that's step one. What I haven't gone through here is step two is, okay, so what's the roadmap? Right? How do we develop nuclear power and propulsion? How do we develop the quantum communication and quantum remote sensing? We know we want to have those capabilities. What is the strategy, right? And there isn't really an easy answer here because that varies a lot. That's on a case-by-case basis, right? For example, I can tell you that we want to invest in quantum information sciences. That includes quantum remote sensing, quantum computing, quantum communications, quantum navigation, right? Our strategies in each one of these areas are very, very different. Very, very different. Like, we are investing quite a bit in quantum communication and quantum remote sensing because we have a very unique approach that we've demonstrated works very well. So we're running with that. We're investing more in that, right? Quantum navigation is further out. So what we're doing is we're partner with some smaller companies that have very innovative concepts, and we're helping them understand the mission needs because they have the technology, atom interferometry, things like that. But we understand the mission, how it needs to be applied to advance that. It's going to take a little longer. In quantum computing, we're basically investing in algorithms that solve problems that are of interest. We're not investing in building quantum computers because there's a lot of companies, Amazon, Google, Microsoft, they're investing on those. So we are partnering with them. We understand what they're doing. We understand the architecture of their quantum computers, and we design algorithms to take advantage of that. So very, very different from each one of those.
Hello, I'm Julian from Austria. A lot of fascinating capabilities you outlined there. A lot of cool things we can do. I'm interested in your and Lockheed Martin's view on how are we going to be able to do these things sustainably? Because if we think about mega constellations, all these new things we're able to do, it might not necessarily be sustainable.
Yeah, that's a great question. And yeah, the whole question of sustainability, we're approaching it in two ways. From the systems that we build now and developing now, we are choosing partners that adopt sustainability metrics and so on. We're adopting those ourselves, and even the way we build things, the way we power things, and so on. When we think about the future and how these systems are going to impact sustainability, then I go back to that geo-health that I mentioned to you, and there's a whole area in that aspect that we assess the impact of these technologies that we're developing, the impact on Earth, the impact on sustainability, the impact on the environment, the impact on society, right? Again, a broad answer. It varies from case to case. Yeah.
Hi, thank you. Do you want to go?
No,
Yeah.
you go first.
Okay, it's a very quick question. My name is Ryud. I'm from Israel. We met earlier. Right. My question is about the habitat situation on the moon, because you had this nice slide, and I was wondering if you're investing in materials to build a habitat, and specifically, are you interested in cement or moon regolith, for instance?
We're definitely interested in moon regolith. A few years ago, we were investing actually quite a bit with some of our customers, NASA in particular, on in situ resource utilization, and we developed some interesting technologies and demonstrate some capabilities in that area. We haven't been doing as much in that area over the past 5 years or so, but it's now going to start to pick up again in light of that being one of the areas that we identified here.
Hello, good evening. This is Victor from Demo Space. Thank you for the presentation. I was just wondering, in my short career in the space industry, I have noticed with regards to technology transfer, the defense industry being less receptive to technology transfer from commercial space as opposed to other associated industries like automotive or something else. Would you have any advice for commercial space industries to commercialize something directly towards defense right from the beginning of a project?
Can you repeat the last part? Towards what?
So, would you have any advice for companies to sell something directly to defense as opposed to something more commercial like automotive? Right from the beginning of a project.
Yeah.
Thank you.
Yeah, thank you. That's a great question. So from my experience, we're not inherently averse to commercial companies. To the contrary, we reach out quite a bit to small companies, commercial and otherwise, to try to understand the technology and see how can we fit into our needs, right? As the R&D lab, it is my role and my team's role to understand the state of the art and then make recommendations, right, that to solve particular problems in different missions, right, this is what's available. This is the risk associated with that. And we don't do everything in-house. We don't want to do everything in-house, but we do need to understand what's the state of the art and who are the A players, right, in industry for that. So we actually make a lot of those connections there. The difficulty that we've seen over the years is that the space business and the space environment has some very unique characteristics, if you will, right? The environment is very harsh, right? It's also a different environment that these systems operate on. Generally, you don't have the luxury to go make a repair. Well, that may change, but in fact, it's very expensive to do that today, right? So generally, you need to design something and you want to have a very good confidence that it's going to work. So what that has driven us, and when I say us, it's not just a company or not a company, it's basically our customers and the industrial complex, right? Is to develop these processes over the years that are, in a sense, best practices, right? But these processes, they get accreted. You are always adding something, and then they can become very cumbersome and very expensive. So every now and then you need to kind of clean the house and go, do how can you shorten that? But it does not negate the fact that it is still a harsh environment. It is not easy to go make a repair. If you make a mistake, in a lot of cases, you lose the mission, right? It's not that uncommon that we hear that people lost satellites, right? Or that you launch, I don't know how many CubeSats, and only 4 out of 10 worked, right? And this and that. So I think what we need to reconcile here is the rhetoric that, hey, take risk. I want you to, in the end, we want to take risk. We want to try things out and this and that. That's the rhetoric, right? And then the reality is when things don't work, people are not happy, right? Customers, either government or commercial customers are not, they're not happy, right? So how do you balance that? And I think that's the trick for the commercial companies, right? If you're going to work with the, traditional defense contractors, right? We have very stringent requirements that we work to. And the system have to work. There's no halfway about it. It has to work. So as long as you understand that and you can be sensitive to that aspect, right? Because what probably you're going to be pushed towards is maybe a higher level of testing, higher level of modeling, a higher level of understanding of your system and worst case analysis and failure mechanisms, right? So that you can convince yourself and your customer that this has, a certain probability of success here. That's really is the gist of it. In a sense, I like to see it from the positive side. We all have a common goal. We want this to work, right? But you're probably going to see high demands on that you probably wouldn't have if you're going to sell your product to an automotive or even aircraft application, because those can land or those can go to a repair station and be serviced, right? So very different environment there.
Hello, I'm Michele Lissoni from Italy, and I was wondering, being a defense company, does Lockheed Martin believe that there is a trend towards an increasing militarization of space? And if so, what defense solutions are you preparing for that scenario?
Yeah, interesting question. No, it's not that there is an increased militarization of space, but there is definitely an increase, and that's, there's data that shows that, right? An increased number of space assets, and the space is getting congested, right? You just have, more and more players and so on. And we have had, especially over the past few years, some close proximity, almost collision, if you will. And I think the question, previously somebody had a question about policy and so on. The policy is lagging behind, right? We're running ahead as an industry, as a community. We're building more spacecraft. We have more companies, more players, right? And we're deploying all these assets. And where is policy helping us to play nice together, if you will, to avoid a collision? I think that's really what's happening. It's not the only area that is happening, right? Automated driving cars, right? The technology is ahead of policy, and it does raise a number of questions because of that.
Okay, I think, is it an easy one? Okay, be loud, Douglas.
So, yeah, we do hear a lot about that, right? And NASA, I think NASA is playing just a fantastic role, not only in driving the technology and the capabilities on that, but also driving this commercialization of space, right? If you look at the NASA roadmap for space exploration, right, that starts with the moon at the gateway and then Mars and so on, there is even the way they disperse funding, right? They enable a lot of these what's called new space, these companies, to become viable, right? Without NASA, the business case for fully commercial is not quite mature yet. It will get there, right? Yeah, but we're big believers in that. We're partnered with NASA. And I gave you 2 examples here, right? With the Lunar Mobility Vehicle that will provide mobility services for basically any company to use. And also the Parsec for lunar communication, lunar navigation. For manufacturing? So let's see. As I mentioned, in a few years ago, few years back, maybe 5 years ago or so, we were investing quite a bit on in situ resource utilization and how to extract water and generate water and oxygen in the moon. We haven't been doing as much right now, and we're evaluating if we need to resume that. Yeah.
Okay, I have a non-technical question for you.
Right.
Goes more to the heart of, you work for a private company, you have stockholders, you have intellectual property, but yet you're here today standing talking about kind of these visions. Is it strategic to share those visions, to sort of drive the thinking and the processes, not just within Lockheed, but more broadly?
Oh, absolutely. Yeah. From the day one, when we started working on this and then discussing with my colleagues and the executives in the company and so on, this is about a vision for space. It's not a vision for Lockheed, right? Of course, I was very open with you in terms of how we're using that information, right? As we identify these areas, we're starting to invest because we believe those are going to be important for the future of space. But this is a vision for the future of space. And as I mentioned, I think I was very open about that too. We probably got a lot of this wrong. So I'm interested in knowing what your thoughts are. What do you agree with? What you don't agree with, right? And how do we as a community move towards a future that is better for everybody, right? How do we really bring humanity into space and expand humanity beyond Earth?
Okay, so then that's what I wanted to hear, because that's hopeful that you're setting the tone. It's not just predicting, it's envisioning. But my experience so far with ISU is there's future leaders here. Right. What could you say to them? What would you want to say to them in, hey, 2050, what can you say to get them there, to get them focused, to get them energized? Is there anything you could offer them that would help them on their journey?
Well, so I offered you this vision, right, which is in a sense very risky, right, because we're probably getting a lot of this wrong, right? And what I ask you is just think about this, and the things that you agree with, let's find a way to partner and move it forward, right, from wherever you are, right? Because as I said, this is not only Lockheed, this is not only NASA, this is not only the US, right? This is the world. And from your position, for the pieces you agree with, how do we get there? Help us accelerate that. We have a lot to do. There's a lot that we don't know, right? Even about the sun, my team has a tremendous history of studying the sun, and there are still some fundamental questions, right? It's a star that's so close to us, drives the environment where our spacecraft operate, and there are some fundamental questions that we really do not understand. Right? And taking 40 years to get to Pluto to do a mission, come on. How can we get there faster, right? And advance knowledge.
Thank you very much.
You're welcome.
Thank you for this evening. Give him So we have an opportunity again to move out to a reception. I do want it duly noted, this is the least late we've ever been. So let's take advantage of it, and that way everybody can get out of here at a more decent time. So thank you very much again.